Hello, everyone. I really love how Anas's keynote just a second ago basically said, 20% at least of what I'm going to say today. And I think it's a common theme that we're going to see throughout the show. What are the real practical advantages of Zephyr and the structure that it brings? And that's what I'm going to talk about today. And I wanted to open up with a quote. That's a quote from Tesla. Our electrical and thermal engineering teams remain hard at work designing, developing, and validating 19 new variants of controllers in response to ongoing semiconductor shortage. I think it's a very powerful quote. I mean, of course, it's a brag as well, but it also highlights a real problem that everyone's facing. I think everyone here in this room has had this anxiety, whether we're going to be able to ship products, whether we're going to be able to build the things that we want in this uncertain environment that we have today. And that uncertainty seems to be here to stay, at least for a longer while. But also kind of uncertainty is one thing, but another thing is the agility and the ability to react to those uncertainties. Everyone would want to be able to pull off what Tesla's doing. They're kind of rebuilding their solution as they go. They're capable of shipping cars when nobody else was able to do that. And of course, it doesn't only go for cars, it goes for all other sorts of products. So how does Zephyr help fix this? Well, I mean, obviously this uncertainty that I'm talking about has a number of challenges it presents, but also kind of opportunities how we can improve development flow. One of the things that we need to have when we want to react to changes quickly is the flexibility, the portability to move between different hardwares quickly, to be able to react to those changes. We also want to, and I think kind of everyone in this room will agree, and that's what my company is kind of really focused on trying to do, is making sure that development becomes more and more software-oriented, that we do software-first development, that we don't wait until hardware is ready to actually get started with doing things. We also need more transparency. We need to understand what's going on. We need to see potential threats. We need to identify bad actors and identify vulnerabilities and so on. And of course, we just need to understand our software better and know how to improve it, how to improve our quality metrics. We need to measure things. We need to be structured about it. And of course, this is kind of not always trivial to achieve in the hardware world, because there's a lot of boards, there's a lot of chips and so on. But many of them are not really applicable to our use case. Some of them are vaporware, others are not perhaps consistently documented. There's a lot of uncertainty related to this. So if you want to test out some software, if you want to know if something's possible to be run on a specific board, well, typically your way to check if that really is the case is just to turn the board on and plug it in and flash it with some software and see, right? But that's not really scalable. You can't really take that and scale it up to tens and hundreds of different hardwares and different kind of software payloads. And also, if you want to just learn about this kind of ecosystem, this capacities that are there versus things that seem to be there but don't really work, it's very hard to achieve this consistency. Well, fortunately, Zephyr comes in, right? And that's what I'm saying, where many of the previous keynotes have already said this. Basically, Zephyr is structured. It gives you this framework in which you build things not by hacking them together, but by, well, making them into a consistent whole. And those abstractions that are in Zephyr are partly related also to its multi-vendor nature, multi-architecture focus, where we're trying to find the right abstractions because we need to target different hardwares from different vendors, and everyone's collaborating to achieve this. I think this is super important because it results in the right level of abstraction. It doesn't result in over-specialization to some specific needs and goals of one company. So it's a difficult thing to achieve, but it's also very valuable. And I'll try to show you how. And of course, Zephyr gives you this data, right? There's YAML files describing boards. There's device trees, of course. I'm a huge fan because they give us a lot of information about the hardware. There's just even the way the repo is organized and the way our discussions around this are organized. All of this is kind of a very valuable source of information. You also get tools, right? Zephyr is not just an operating system. It also provides tools to handle device trees and so on and so on. So overall, it's a whole ecosystem. There's libraries that we have a way to manage in a consistent way. All of these features, all of these things can be leveraged to build something cool. So what does Zephyr really enable? I'm going to tell you very briefly about one project that we kind of started some months ago, and it's been going really well. I'm not going to focus on this because there's going to be a separate talk about this tomorrow at 9. But the Renode Zephyr dashboard, as we call this, is essentially an interactive CI dashboard that's running 5 different binaries at this point across hundreds of different Zephyr platforms in simulation. We have this simulator called Renode, and since it kind of maps pretty well to the device tree data that we can get from Zephyr, as a result, we are able to run hundreds and hundreds of tests very consistently, very repeatedly on different Zephyr commits and just generate those kind of data points, like whether something's passing, whether it's compiling, sometimes it isn't, so that's kind of also important feedback information. But generally speaking, even we were surprised. Like, we knew that this was going to happen, that we were going to be able to do this in a scalable way, but even we were surprised that we were able to get to 170 different hardware boards where we can run demos and simulation. And it's all based on the Zephyr device tree data. And we can compile those with like one line, right? Like West build and the targets. And we can take that, run in simulation. We generate the simulation files from the device trees. It just works. So that's kind of awesome. And this is, of course, the testing aspect of what I described. This is, of course, very important to do. But we thought, OK, this is cool. How do we take this further? How do we take it a step ahead? So we decided to build something that I'm going to introduce today, which is called RENODEPEDIA. And it's basically an interactive encyclopedia of hardware that tries to address all those kind of problems and opportunities that I've just outlined earlier. So you can kind of browse different boards, different SoCs, and see the vendors that sell them, and well, just learn and reproduce things on your own. A little bit of motivation behind it. So essentially, you can see that hardware is modular. Anas was saying this just a second ago. If you build hardware, you typically compose it of IP blocks that are reused. They're similar. They're sometimes the same between different microcontrollers, different families. There is no sense in trying to reinvent the wheel in hardware because validation of hardware is very hard. So what hardware folks tend to do, they take the hardware and just copy-paste it a lot, right? And rearrange it and kind of rebuild it into different application-specific solutions. That makes a lot of sense. But that information isn't necessarily always consistently passed on to the software people, right? And it's nobody's fault, right? It's just the disconnect between those two worlds where sometimes you have to like almost reverse engineer, like what's what? You know, how are these two microcontrollers related? Many times in our careers, we've been kind of looking at things and saying, oh my God, this is the same thing. Like, why didn't anyone tell me? So this kind of disconnect is kind of interesting because you can actually bridge this, and Zephyr does a very good job at doing this, right? Because Zephyr needs to extract this information, those kind of abstractions, into structured data to be able to map drivers, right? So Zephyr has this data in device trees, and this is kind of really, really useful. So we kind of found this interesting feature, and we thought, OK, what do we want to do here? Well, basically we want to catalog hardware in a very consistent way. We want to make it a connected ecosystem where you can navigate between things, you can discover that things are similar or the same, you can see the dependencies, you can kind of explore what's running with what and so on. And the cool thing is that since we also have Zephyr that we can use to build different kinds of demos and libraries and so on, we can take that and run that in simulation so that you don't only get hardware data, it's not just something you can browse. It's also, you know, software that you can really run, and this has been tested so that you can actually just go and see for yourself on your own computer. And of course, like, the important thing was that we don't have to like hand code everything, that we can automate this process. So that's kind of one of the resulting screens. What you can see here is a board view where we try to present as much data about the board as we can, the board and the software that we can run on top of it. And in some sense, it corresponds to our CI system, the Zephyr dashboard, but it presents this data in a much more kind of focused way to show you like what it's all about. One of the things, of course, is the binaries, the demos themselves. We can run different kinds of libraries, including TF-Lite Micro, including micro-ROS. That's not yet on the dashboard in RENODEPEDIA, but it's going to be there soon. And generally speaking, it's kind of a quick start, right? You can grab this and get started very easily, and you'll be able to see that it's supposed to work, right? Because we kind of have this information in RENODEPEDIA. And I think it showcases the ecosystem aspect of Zephyr pretty well, because like we were talking in the TSC meeting about how do we show that Zephyr is not just an RTOS, it's an actual ecosystem of different solutions and libraries and middlewares. And well, we have a way to kind of demonstrate this. As I said, you can actually run these things locally. You can just execute those commands, like pip install a helpful script called renode-run, and then you'll be able to just run a demo yourself on your own computer. So what renode-run will do, it'll download Renode, it'll just grab the artifacts from our CI system and just execute it. You can, of course, compile your own binary as well, but that requires you to also install the Zephyr SDK and do a bunch of other things. But yeah, well, essentially the binary is going to be something that we compiled for you. You're going to be able to reproduce the results locally. And the tool's open source. You can check it up on GitHub. But if you don't want to install anything, you can also go and use the Renode Collab functionality that we built. And this functionality is essentially something they can use to run things in the cloud. Like it's just no installation needed. Google provides the compute power to do this. And we have pre-made collabs, like we have hundreds and hundreds of collabs, thousands perhaps, where you go to the collab and you run the specific binary on a specific board, and it's just there. I'll show you in the next slide. We also are working with Google, because we're a Google partner, to enable people to also run these things in GCP directly, not through Google Colab, but like on a dedicated machine, just spin up a simulation, do some testing and things like this, all with one click. And these kind of things are really great for like education and teaching students and so on. That's what it looks like. That's a nice dark themed collab where you can see, perhaps, I don't know if you can see from there, but on the bottom you can see the result of the execution. It's a hello world. And we basically take this, open this, press run, and you're going to see that on the bottom. And of course, we also give you pre-built artifacts from this entire endeavor, including as Kinema screencasts, so you can just play it and see it kind of play out in real time. We also have SBOM data for all of those binaries, kind of appreciating the way that Zephyr kind of pays attention to these things. We have all sorts of other artifacts, including robot tests. If you know what a robot is, you can actually see for yourself how a log from this kind of test run looks like and get the robot script to kind of take and improve, perhaps, extend to build your own tests. We also have runtime data. Here we're showing a trace on the RISC-V platform, and this is actually pretty recent. I think it's really, really cool because we can generate those traces for RISC-V today. We're going to be able to do that for all the boards very soon, and this, of course, tells you a lot about how the software behaves. All right, but that was kind of the board view. But the important part of what I'm talking about is indeed in the other part of RENODEPEDIA, which is the SOCs. The SOCs are actually something that most people eventually focus on, because if you're building a product, you will start with a dev board for sure, but eventually you'll build your own hardware. And that's where you want to understand how different SOCs are related and which one you should pick and which one supports what and so on. So we built this kind of interactive screen for preview of SOCs. And the important thing about this is, well, we're presenting the memory map here, of course, that's one thing. But we're also mapping this to the Renode peripherals that model those IPs, right? Now, again, we can do this because we have the device tree data and the compat strings and so on. And we're also working on just mapping it to Zephyr drivers. We know it's doable, it's just we haven't managed to do it before the summit. But essentially, you'll be able to go and see the driver, and cross-reference things and so on. So I think this is really important because, the SOCs are actually what you end up working with for your products, right? And having a way to explore them consistently, I think, will be very, very interesting. And you can also see what boards support this SOC. So like you can see different dev boards you could buy to test out this SOC. And you've seen this little chip kind of icon there on the top. This is actually automatically generated, right? We have a CI that generates it from the signature of the chip. We know how many, how big the enclosure is and so on. We can essentially build it out. This is a KiCad script that generates it, right? And in a broader sense, we are working on an open source database of components which you can use to not only generate like chips, but also entire PCBs. These are a few Zephyr-capable PCBs that we've been involved in building or helping bring Zephyr to, and we have the design files for them because of that. So we can generate this from KiCad data. We're actually working to also enable not only doing this from KiCad sources, but perhaps also from Gerber files. I'm really excited about this because that we can generate like 3D interactive visualizations, we can kind of highlight things and so on. This is not yet integrated into RENODEPEDIA properly, but this is something that is really advanced, and I'm super excited about this. And if you go to an even broader perspective, we want this to kind of not be the end of it. It's not like Zephyr made some great kind of abstractions. We can just read that data and do something cool. We want this to proceed in that direction. We are involved in CHIPS Alliance and RISC-V Foundation. RISC-V is focused on building, configurable hardware, self-describing hardware that gives you this information. You don't have to extract it anymore. You can kind of get it out of the chip itself. We're looking at topics like hardware bombs, like how do you kind of more efficiently explore what's inside a chip. We're also working on open source IPs. We're building open source memory controllers, CAN controllers, working on real silicon-focused projects where open source IPs are being used. And we believe there's a huge future to this. I mean, obviously, it's still years ahead in a sense, but we want to gravitate towards this kind of environment, this kind of universe where building chips is much less clandestine. It's much more understood and kind of structured than it is today. We believe there's some great progress that we're very excited about, and yeah, that's why I'm involved in kind of bringing Zephyr and RISC-V and CHIPS Alliance together. So summarizing, we want to push the world towards a more software-first development. We believe that software is powerful. We've seen how open source transforms software to be much faster. Hardware can benefit from this too. We believe that you can essentially guide your hardware development process with your software work, right? If you start software development early, perhaps in simulation, you will start seeing patterns, you will start understanding what you really need on the hardware side. And the co-design aspect is growing a lot. Like, it used to be, not really the main focus of Renode in our company. Like, gradually, especially with the advent of machine learning use cases, this is a necessity. I mean, you can't really follow the speed at which machine learning is developing without being able to do this co-design. And so more and more people come to us and say, oh, we really need to kind of be faster. We need to think how we develop the hardware and the software to match our needs. And Zephyr is a great enabler for this. So, action items. Well, if you're trying to convince people internally that Zephyr is great, well, hopefully I've given you a few arguments. If you're already convinced your company is using Zephyr, you're all in. That's awesome. Let's talk about how we can kind of use this to make the ecosystem better. And of course, we'd love to talk to you and see how we can improve RENODEPEDIA and improve our coverage and perhaps, add more data. And yeah, go and see it for yourselves. And thank you very much. That's all.